Should we go ahead and get started? So welcome everyone to this second week of the QFT and Geometry Summer School. And today we're very happy to have Fabio Apruzzi from Oxford speaking about geometric engineering and holography at 6D and 5D superconformal field theories. Thank you, Fabio.
Thank you for giving me this opportunity to give these lectures. So, as Ken said, my lectures are going to be about geometric engineering and holography of 6D and 5D superconformal field theory. By the way, can you hear me well?
Yes, it's good. Thanks.
And well, in particular, I mean, also if you have questions, please interrupt at any time or just ask in the chat. So I will basically first travel a bit in time and go to the 90s, where basically all this geometric engineering from brain started. So, and as you may remember, in the 90s, there were many famous things like this, so many famous objects or many sports things like this. But there were also other famous things that have been created in the 90s or have been like developed in the 90s, which are like brains and strings on brains. And in particular, these like two fundamental paper. So this, especially this one, and then also this one for other particular constructions. And the construction I will talk about are basically based on the paper by Anani Witten from 1996. And in particular, they are T-dual version of these constructions. But let me tell you about the plans of these lectures. So the first lecture is going to be about 6-dimensional superconformal field theories from M theory and 2A. And then I will, in the framework of M theory and 2A, it's natural to also have the holographic limit. So it's natural to have a near horizon limit where we have ADS solution. And these, so this lecture is going to be based on this, mainly on this reference. And also another reference which I indicated. It's not a complete list, but together with the papers cited in these other papers, it's probably a good list of reference. And then I will talk about 5D in the second lectures, and the relation between 6D and 5D in the third lecture. Okay, let me start with lecture 1, which is the lecture of today. So the lecture today is, as I already told you, it's about 6D superconformal field theories, and now they are constructed from M theory and type 2A. And then I will also introduce these holographic constructions. So we start by an introduction, and then I will introduce the 1,0 supersymmetry together with the fields of and the multiplets of 1,0. And then I will talk about the geometric engineering in M theory, and in particular in 2A. I will talk about how this brain system can be manipulated and how we can access the moduli spaces of these 6-dimensional theories. And then I will introduce the linear horizon limit. So I will talk about the holographic limit of this brain construction. And finally, I will talk about some computation that one can do by using holography. So if one starts in 6D and one tries to write a free Lagrangian with some like weakly coupled interaction, one realizes that, so let me write, so this is free field. Lagrangian, and this one, some interaction. And if one realizes that by writing this Lagrangian, all the interactions are irrelevant. Irrelevant means that the coupling has masses, has the mass dimension, which is negative. So for example, we can write a scalar with a phi for interaction and a scalar with phi for interaction. So the scaling dimension of the interaction is equal to -2. And also another example, which would be relevant in what I'm going to discuss later, is like if we write an interaction, which is the gauge kinetic term, like this one. And this will tell us that the mass dimension of this coupling is minus this one. So we see that these interactions are irrelevant. So we are facing two possibilities here. I mean, mainly two possibilities. The first one is that there is no renormalizable interacting QFT in D equals 6. The second one is that the free theory plus those weakly coupled interaction is unaffected description at low energy. And I will tell you what later in a second. So let's stick with option 2 for the moment and see what are the possible consequences of having this theory as being as an effective description of something else. So as I told you, this, the effective theory, which is Lagrangian plus interaction, is really a perturbative, so it's really a low energy effective theory. And in particular, if one tries to write a perturbative expansion, this comes with this parameter. So we have the coupling and a scale, so which is like a cutoff scale in the UV, lambda, and L is always bigger. So this tells us that the coupling grows at high energy, and so that the theory is not renormalizable. So the only way to make sense of this theory is if there is something non-trivial in the UV, a strong coupling when G is equal to infinity. And this might be a CFT. So, but the CFT, if it exists, is a non-Lagrangian theory at all energy scales. Moreover, this effective field theory means that if there is a CFT, it UV completes the CFT in the UV. And finally, as I already mentioned, the CFT is really strongly coupled. So the goal is indeed, so we see that with this effective field theory description, it's very difficult to access these regimes. So the goal will be to provide evidence that like option 2, where this theory is effective, an effective field theory description of a CFT in the UV is really the correct picture. And this will be done by introducing this brane system string theory with supersymmetry in order to have control, and also with the ADS-CFT. Moreover, there is a bonus motivation in doing this. And the bonus motivation is that, so by imposing supersymmetry, conformal symmetry, and Lorentz symmetry, this mathematically tells us that the space-time, so the maximal dimension of space-time allowed, is D equals 6. This is also the num. So this is a result by num, and basically num classified all the superconformal algebra. And the superconformal algebra, they exist up to 6 dimensions, space-time 6 dimensions. And moreover, by symmetry breaking or by compactification, so if one breaks supersymmetry, conformal symmetry, or Lorentz symmetry, by compactifying, this can also lead to a zoo of other models. So this is a really, so 6 dimension is a really sort of unifying, so it can be viewed as a unifying theory of like a lot of models. Okay, let me introduce some basics about 1,0 supersymmetry and 1,0 and the fields of 1,0. So what I mean, what do we mean by 1,0 is that we have 8 real supercharges, which are labeled by Q alpha. And these 8 real supercharges, they come together with an R symmetry, so with an SU2 R symmetry. And the algebra of this is given by for the sigma are the Pauli matrices, and then the commutator of the R symmetry generators is just the SU2. The SU2 algebra. So this is just the commutation between the R symmetry and the supercharges. But one can actually write the massless states of 1,0 in terms of representation of the SO4 subalgebra into SO5,1. And this representation, they come with 2 spins. So SO4 is basically SU2 times SU2, and the representation of SO4 come with 2 spin J1. So in 60, we have a tensor multiplet. A tensor multiplet is given by a 2-form field, which has spin 1,0, plus 2 fermions, which transform under the SU2 R symmetry. This is 0. And then we have a scalar. Moreover, we have a vector multiplet, so we can write a vector multiplet. And a vector multiplet in terms the spin, the SO4 representation given by 1/2 plus 1/2 plus 2 fermions, which also rotate under the R symmetry. And then we have also hypermultiplet. Hypermultiplet given again by 2 fermions. And this is complemented by 4 scalars. And in general, there's also a graviton multiplet. The graviton multiplet is given by the metric 2 fermions, so a vector of 2 fermions, and so 1,1, which is the metric, plus 2 times 1,1. And then we have another 2-fold field. As we can see, this 2-fold field is different from this 2-fold field, and they differ by being self-dual or anti-self-dual. So this means that DC and DB. Moreover, we will consider multiplet. So I just introduced the graviton multiplet because I wanted to align this difference between self-dual and anti-self-dual. But in what I will tell you, the gravity is decoupled, so we don't have this graviton multiplet. So this graviton multiplet is not there. In the theory, I will talk about. Moreover, in 6D, there is no real, modular space of vacuum in the math sense, but still one can give VEV to this scalar, the tensor multiplet scalar, as well as the scalar, but I will talk about later. So this is the so-called tensor branch. We will give scalar, we will give VEV to the scalar of the tensor multiplet. And as a last comment, I want to tell you that one tensor plus one hyper, they give rise to a 2,0 tensor multiplet. So we can have a theory with nth number of tensor with this constraint. So this is H is proportional to dB. It will have other term, but I will talk about them later. So H is anti-self-dual, so it respects this equation. And in particular, it takes values in a lattice in 6 dimensions. And it takes value in this cohomology group. So if we couple the theory to a 6-dimensional manifold, it will take value in a lattice lambda times R. So the H, as I told you, it's dV plus some non-exact term. And if we integrate dH on a 4 manifold, this will give a charge. In particular, it will give like a vector of charge. And this vector of charge is basically a vector in a lattice. And by tadpole cancellation, this tells that there are strings, so B field, which are like Poincare dual of these 4 cycles. So this is M4. It's a 4 cycle in the 6-dimensional space. And this is basically Poincare dual of that 4 cycle. And the strings are charged under B. Sorry, the strings will fill the Poincare dual of that 4 cycle, and they are charged under this B because of tadpole cancellation. So this will give rise to a lattice of charges. Again, the lattice is this one. And the tensions of these strings will be given by this. So tension of EI is proportional to omega ij. Well, omega ij is the Dirac pairing. So it's the pairing in this lattice. And then we also have that 2 vector of charges, they pair like with this pairing.
The question in chat.
Yeah.
If H is in cohomology, does that not mean that H is closed?
No, H. No, the H is not closed. So there are no. So yeah, I will show you that it's not closed. So DH is actually not 0.
So
it's not, I mean, it's not really. Sorry, yeah, this is a misleading. It's not really in commodity. But DH is not closed. But I will show you what the exact expression of DH.
thank you.
So we can also write a pseudo action in the tensor branch. And the pseudo action is a pseudo action because of this set quality constraint, so anti-set quality constraint. So in type 2B, like in type 2B supergravity, where we have F5, which is equal to alpha F5, we don't have really an action, but we have a sort of pseudo action where we have to impose this constraint by end. So, and I wanted to show this pseudo action just because of the following reason. So we see here that the coupling of the kinetic term is actually dynamical. And it's dynamical, and this is a consequence of the fact that there are no mass deformation of 60 superconformal field theory. And moreover, if we want to write like a sort of coupling which would be scaling variant in the UV, we need the coupling of the Yamis coupling to be dynamic. So in the tensor branch, this is actually really a verb. So when the action makes sense, this is the verb. Moreover, and this is related to what Kentaro explained in his last lecture, that we have this topological coupling, and this topological coupling is there in order to cancel reducible gauge anomalies. So, and we see here that if one varies this action, we can write the expression for DH, which is DH is proportional to 24. So where we have this is proportional to this curvature, plus if we couple the theory to background fields like background for the global symmetry, the R symmetry, or the tangent bundle symmetry, this will have other terms. And this term is necessary if we want to, as anticipated, is if we want to cancel the reducible gauge anomaly, and by what is called the Green-Schwarz West anomaly. Okay, let me start by the core of this lecture, which is the geometric engineering from M-theory and type 2A. And so let me start from M-theory. So in M-theory, we can start from N and 5 branes, which fill the first 6 directions. And so they are point-like in, well, we pick a direction here where they are point-like in the 6th direction, and they have like an orthogonal 4 directions. So what we want to study here is the low energy volume theory of M5, which defines a 60 theory. Moreover, since this is 4 directional non-compact, and the gravitational coupling is proportional to the volume of these 5 directions, this means that gravity is the coupling. So the first question is this really a consistent background of M theory? Well, the answer is yes, and it preserves one of, so 16 supercharges of the 32 supercharges of 11-dimensional supergravity. And the metric of this background is given by this expression. So where H is basically this function, and it depends on X6. So the orthogonal direction, the orthogonal, so the 6th direction in this picture. So the flux is, let me write it like the Bianchi identity, which determines the flux. So this is the flux of this solution. And moreover, we can see that this solution has a SO5. So the isometry of this space, so the rotation of this coordinate will define a isometry of the field, no, the isometry of the background. And this isometry of the background is dual to, well, it actually realizes an SO5. Let's see. Moreover, when all the M5 branes are collapsed, we see that there is no scale in this appeal. So there is no scale anymore, and everything is either 0 or infinity. So this is like a first evidence that these backgrounds engineer at 2,0. Moreover, the second evidence is that we can actually write the near horizon limit of this solution, and the near horizon limit, this solution looks like. So it looks like an ADS7 times S4. So this is the S4 method. And where LTH is basically proportional to the number of. So this is another good evidence that we have A, so by via the CFT, this is a good evidence that we have a CFT dual via this near horizon limit. Okay, but let me focus on 1,0 theory. So 1,0 theory have 8 supercharges. So, and they will be basically a generalization of these 2,0. So they have 8 supercharges, and a superconformal point, there will be additional 8 superconformal partners. We can start from M theory again, and we can mod out the orthogonal 4 dimensions by a subgroup of SU2, so gamma is a subgroup of SU2. Particularly, it's a subgroup of SU2L, where SO5 is basically broken to SU2L times SU2, right? So the gamma acts on the like the 2 complex coordinates of in this orthogonal direction, like this, where omega is a generation is a generator of gamma. And there is actually a classification of this SU2 subgroup, and this classification is also called the Mackay correspondence. So we see that with the so we can associate an ADE group with an ADE algebra with these finite groups, so ZK, DK, and TO. So this T tetrahedral O is O. So E is equals hydral, you know. So, and in particular, I will also comment that the SU2R is basically what realized the SU2R symmetry of the 1,0 theory. Moreover, we can write it for A and D type. We can write a S1 fiber metric. And this S1 fiber metric looks like this. Well, this is the S1, the 10 direction is the S1, and R is the radius of S1. And now, since we have written this circle, we can reduce to 2A on this circle. And M theory on this background, C2 mod CK, when reduced on this circle, gives rise to K this circle. And the M5, and if we reduce on an orthogonal S1, this will lead to an S5 reduction. So the geometry of M theory, and so let me summarize the geometry. So geometry looks like this. So we have an S1 fiber. So there is actually a deficit angle of this S1, which is fiber over dr3. And the deficit angle is 2 pi over 3. And this deficit angle is what is responsible for like the K DC. And moreover, we have also n NS5 branes. And this is the picture that we have in 2A. So in 2A, we have NS5 branes filling the first 6 dimension, plus a D6 brane, which also fills an orthogonal direction. It's the 6th direction.
Excuse me.
Yeah.
The D6 branes, they're created dynamically because you don't put any branes just on the circle, and so you just take M theory on the singularity on a circle, and you where do the D6 branes come from?
Yeah, so I reduce on the circle, which is orthogonal, which is sorry. So the circle is inside the C2 mod ZK. And the fact that we give a deficit angle, the fact that it has a deficit angle will give rise to a singular object in 2A. And this singularity is interpreted as the D6 brane singularity.
I see. Does the singularity source some flux in?
Yeah, I mean, you will get the metric and the R Ramon form for the so if you write like if you write all the metric in 11 dimension, you also get the Ramon form of on the D6.
Yeah. Thank you.
So this was just be sketchy, but that's just to highlight how it goes, the procedure. But what we can do into A is we can add another object, which is the 8 branes. And the 8 branes, they fill this dimension. So they don't fill the 6 direction, but they fill the 7, 8, 9 directions. So by this, we see that the SO3 axometry is preserved. Supersymmetry is also preserved. So we have the same supersymmetry. And moreover, D8 is electrically charged under C9. And the dual of this C9, so the magnetic dual of this C9 is basically leads to like the Roma's mass, which is F0. It's called the Roma's mass. So we allow also this F0 to vary and to be turned on in the background. So when this F0 is turned on, there is no M theory. This is a so we cannot uplift back. Okay. So let me tell you how from this brane system one can get the content of field of 1,0. So let's start from this example. So this is I now separated all the NS5, and like I also have D8 branes. So let's start from this. This example brane system. So if we separate the NS5 branes, what they lead is to the tensor scalar. The tensor scalar will be given by just the difference. So if we have this I plus 1, this will be only the difference will matter. So the difference in the 6th direction will give rise to the tensor branch scalar. And moreover, also the difference of B field will give rise to the dynamic of B field. So the NS5 branes, so in their volume, they carry this 2-4 field instead of a gauge field. So this is like an M5 branes in theory when reduced on a circle. So there are also like scalars of the NS5, which are the orthogonal direction with respect to NS5. But this, just to comment on this will be responsible for the decoupling via Stuckelberg mechanism of the U1 of the D6 brane Born volume theory. So I mean, I don't have time to review this, but just to mention and in what I will consider later, the U1 will be basically decoupled. So I will talk about SUK theory instead of UK when I talk about D6 brane. So let's focus now on the 6 NS5 intersection. So the 6 brane, so a stack of the 6 brane defines a 7D supergamma theory at low energy. So, and if we have like an NS5 in on a fixed locus in this X6 dimension, so here, this NS5 acts like a sort of domain wall for this 7-dimensional theory. Okay, so we can start from this 7-dimensional theory, and we can write the Born volume action for these D6 branes. The Born volume action will be given by this. But so this is a complicated expression, but what matters here is this term. And if one actually expands in power of LS, in particular takes this limit, yes. So we view the D6 brane theory at low energy, where the length of string is looks very small, and also want flat space, and B on the D6 goes to 0. What we get is basically a UK super-Yamist theory with action, which is given by the 7 squared. What GM is basically given by this. So then the NS5 branes, it implies that we have non-boundary condition for the vector of the D6 brane. So what is so the non-boundary condition are as follows. So we have that F mu6 on the NS5 is equal to mu A6 is equal to 0. So the value of A6 is fixed at the locus of NS5. Moreover, the NS5 divides the 7D super-Yamist theory into 2, together with non-boundary condition into 2. Gauge field strength, where X60 is basically coordinate in 6 dimensions, and X6 is the orthogonal coordinate, so the 6 coordinate is one. So the UK theory would be then equivalent to UK 60. So from a 7D theory, okay, that's UK 60 left times UK 60 right. And we also have string excitation. So we can have string excitation, so fundamental string connected from one D6 brane on the left to one D6 brane on the right. And if one writes down the chain pattern index, we realizes that the excitation in the 7, 8, 9 direction will give rise to bifundamental hypermultiplex. So the bifundamental comes from the chain pattern index on the left and the right with respect to these two. So I kept the U here, but as I told you before, the scalar of the NS5 will decouple the U. So moreover, we have also Dirichlet boundary condition for the scalar orthogonal to the D6. So these are fixed to 0, so they don't contribute to the theory. And to summarize, what we have is that if we have a finite segment, we have a 60 gauge theory, whose coupling is given by the tensor scalar. If instead we have an infinite segment, this infinite segment will give rise to flavor because its coupling goes with it's the inverse of the length of that segment, which is X6, and goes to infinity. So in this case, the coupling goes to 0. So and then we have a flavor symmetry when the branes are infinite. So as I told you, we can have D8 branes. And D8 branes, since they feel like free non-compact direction, they will also be responsible for the extra flavors. So GMS will go like the volume of these free coordinates, because the D8 brane also fills these free coordinates, and so with the inverse of these volumes will be then will be basically 0 because the volume is infinite. So we can also have strings in this case, strings between D6 brane and the D8 branes. And these strings will give rise to flavor hypermultiplex. Moreover, the D8 brane, they change the value of the Romance mass. So here we have an F0, and here we have an F0. or more precisely, 10 E8. So, okay, so if we now put together the D8 brane with the system of an S5 and D6, we have some consistency condition that we need to satisfy. And this consistency condition, they will come with the Bianchi identity for the F2 fields. So the F2 fields basically tells us about the number of the 6 branes. And if we cross an S5, then there can be a difference on number of 2 branes, which is proportional to F0. So pictorially, one can do the following. So we can have an S3, an S4, S3 in the X6, X7, X8, and X9 direction. So we pick a free sphere embedded in this direction, which surrounds the NS5 branes. And now we can write the flux as follows. So the flux will be given by this. So we have 1 unit of the NS5 brane. And then we have like the F2 flux, which tells us about the D6 brane coming in and coming out, which will be given by this. So they are proportional to this S3. And what this tells, if we integrate on this S3, what this Bianchi identity tells us is the following, is that the number of D6 on the left minus the number of D6 on the right is equal to F0. So by just plugging this into this equation and integrating it on S3, on this S3. So on the left of, so if we come back to this little zoom in of the brane system, we have that on the left ND6 I minus 1 minus ND6 I. So this is I minus 1. So before the first NS5 is I minus 1. In the middle is I, and after the second I plus 1, after the second NS5 is I plus 1. So here on the left of the D8 we have this, and on the right on the D8, so between I and I plus 1, we have ND6 I. Plus 1 equal to F0 plus ND8. So in this case, I just draw D8, but it can be more. So F0 changes because of the D8. So we have this shift in this consistency condition. So now, together with the brane system, so we see that we can write down from this brane system as quiver. And the quiver, so by what I told you already, so we have this content of field from the brane. The quiver will look like this. So with the semi-infinite D6, we have flavor symmetry. With the finite D6, we have associated the gauge groups. So there are hypermultiplets which comes from strings. Here, strings there. So this is the little segment connecting these gauge groups. And then we also have a flavor symmetry coming from the D8 brane, which is, in this case, we have just one brane, which is, it is only a U1. And the general condition is the following. So at each interval, the number of D6 is equal to the sum of the number of D6 of the nearest neighbor intervals plus the number of D8, which in this case I indicate as flavor, but this is really the number of this. And Ni is the number of this. And this in the quiver corresponds to the quartic anomaly. In particular, so this condition is the quartic anomaly cancellation. It's summarized by this for SUK for the SU groups. And it's basically the cancellation of the one loop anomaly that comes from this little anomaly polynomial. So that can be a coefficient, and this needs to be cancelled at one loop for consistency of the theory.
Fabio?
So yeah.
Fabio, I have a question. So you have this 1d8 brane here between these between these two NS5 branes.
Yeah.
And that means that after that, the number of d6 branes goes down gradually. So you have 3 and then 2 and then 1. So if you included, say, another d8 brane between the next pair of NS5 branes, would that mean that it would go down like steeper, so then you would not have the next d6 brane? So what? Okay, so could you also have multiple d8 branes?
Yes.
To decrease that number of ending branes by more.
Yes.
But you can't have you can't have too many. So you couldn't have 2 d8 branes, or like in that case, instead of that 1 d8 brane, you couldn't have like 4 d8 branes because it would decrease it by too many branes at once. Okay.
That's fine. So this will become the new Romance mass. And then you have to work with this new Romance mass if you have another d8 brane.
Right, so that's why it's going down. Basically,
that's
like
why it's going down.
Yeah. Okay. Can you also make it increase basically? So is there a way to?
No. Because if you want to make it increase, you need anti-d8 branes. Because you need to.
Sure. And that's not.
But then you break supersymmetry.
Okay. Thanks.
So if F0 is negative, it actually decreases. So it depends on. So you can have F0 negative and then it decreases, but then you have if F0 positive, also F0 always increases as well.
Thank you.
So as a final comment, we can shrink this NS5 brane together, and what we get is the following system. And this system tells us that the value of the scalar are 0, and this is our evidence that we have a superconformal field theory. Moreover, the other evidence that we have a superconformal field theory is that we really have tensionless strings in this limit, and the tensionless strings will be given by BPS brane, VSD2 brane, which are connecting again between the two NS5. And they are light and tensionless when the NS5 branes are collapsed together. Okay, so we have now set up the brane system, and we can actually do some manipulation with these branes. And doing manipulation is actually a nice way to access the moduli space of this 6-dimensional. For example, the first manipulation we can do is separate the NS5. So we already anticipated this, but separate the NS5 means moving in the tensor range. So it's now F1, I1, I2, I3, I4. So in this case, these are all different things. And we are in the tensor range. And in tensor range, we can write a quiver, which in this case, it's like just a linear quiver. It's always a linear quiver, but in this case, it's a linear quiver, and so the only flavor are this SU3 and this SU3 on the right. So let me zoom here. So to have an SU3 flavor, we need a D6 brane to end on a 1 D8 brane. But if we have many D6 brane, ending on one D8 brane, this is actually more complicated. So it is more complicated to separate in the tensor branch. And in particular, it's not super clear how by separating these NS5 we get down to this brane system. So, okay, so in fact, in a full tensor branch, there is no way to make sense of the following configuration. So when we have multiple ending, multiple D6 ending on D8. And in particular, there is, so in this case, there is no standard gauge theory. Interpretation. So for example, here, so we see that the number of D6, so it's basically changes after crossing a D8. So it's not, what is the gauge theory? And so what we need to do is what is called an Anani-Witten transition. So the Anani-Witten transition is basically so when we cross, we need to cross an NS5 brane across a D8 brane. And in crossing an NS5 brane into D8 brane, a D6 brane is created. So here's what is created. So an NS5 crosses, as anticipated, an NS5 crosses at the end, and then a D6 is created, crossing at the end. And again, this is not consistent. We need to go on, and we need to cross again multiple D6 until we reach the consistent configuration. And the consistent configuration is basically this one. So where we cross 3 NS5 across the D8. So here we see that we have just this crossing of D6 across the D8, and there is no configuration like this in the tensor branch brane system. Okay, so this is the tensor branch, and now we can move to the X branch.
Ciao, Fabio.
Yeah.
Sorry. If I may ask, what is the gauge theory, from the gauge theory perspective, what do you see as you do the reverse of the Anani-Witten transition? Like, is there a point where the gauge coupling blows up, or what happens?
I mean, there is not standard interpretation, right? Because here, so here I will have an SUN gauge theory. If I have, so for example, here I have an SUN gauge theory, but here, I mean, I would have like SU3 here. And whereas here, I don't know what is the interpretation of the gauge theory, because I mean, I have like a discrepancy of D6 brane on the left, on the right.
But on the one, at the starting point, you do begin with a gauge theory.
Well, the starting point is this one, and it's the conformal point.
Ah, okay, I see. So it's
in
all
order
in the
tensor branch to
Lagrangian.
make sense of this, the allowed configuration is basically when you cross, like when all the D6 cross on the left, on the right. So it's really a tensor branch gauge theory consistency condition. It's also dual to the S. The Anani-Witten move is a consequence of the S rule in the Anani-Witten setup. So that's like I think a good way to explain it.
Okay, thanks.
So, okay, let me talk a little bit about the X branch. So the X branch, so we start from a strong coupling from this configuration. And what we can do if we have the segment between 2D8 is sending this segment to infinity. So by sending this segment to infinity, so here we send a segment to infinity, And so what this means is that we are giving that to certain operators. So in particular, the value of this operator will be proportional. Will be proportional to these directions. So this operator will be related to some hypers because there will be strings connecting the D6 brane, and they will be related to some hypers. And in fact, the hypers were given by strings connecting two stacks of D6 and fluctuating in this 7, 8, and 9 direction. So, but let me explain what happens at weak coupling if we resolve in the tensor branch this brane system. So we separate the NS5 brane. And again, here we have a sort of configuration. So I already sent two stacks of the brane to infinity, of the a segment of the 6 brane to infinity, which is this one and this one. And also, if I send this segment to infinity, I can decouple a D8, which is not connected to my system. So I can send the D8 to infinity as well. So I got this system, and I separate the, we can separate the NS5. So we have this system. And in order to make sense of this system, again, we can do an analytic moves. And now we can send two NS5 across the D8. And what we get is this brane system. So this is the brane system where we have a gauge theory interpretation, and we can observe two things. First of all, that the number of tensor is conserved. So it's really another, so it's not, it's really another branch. It's like, it's the X branch, so it's not related to the tensor branch. If we send this segment to infinity. And moreover, the vectors and the hyper, the number of vectors and hyper is not conserved. So because we have changes the rank of this gauge group in the quiver interpretation. So, but what is the general strategy? So the general strategy is we can start from this configuration, which is analogous, is basically this one.
Fabio, there's a question in the chat by Federico Carta. Can I send any D6 brane segments to infinity, or there's some analog of the S rule in this really Hanani written cartoons?
Any, yeah, and you cannot send any D6 brane to infinity. Yeah, you cannot send any. I mean, there is indeed there's a rule. There's a rule in this. So you can send this one, and then you send this one, and then you send this one. So yeah. The answer is yes. Let me read the question. Yeah, I think you cannot send any D6 to infinity. There is a rule in that, and there is an order. Actually, I have an exercise about that later. So, but the general strategy.
Sorry. Can I ask a question?
Yeah.
So when you are sending that D6 segment to infinity, does it matter in which direction you are taking that segment, or? No,
it has to be on the 7, 8. So this segment has to go to infinity parallel to the D8 brane. So it's going in this direction. So this is the 7, 8, and 9 direction.
Okay. I see. Thank you.
Because I mean, because of the symmetry of the system, you can only move in order and not breaking supersymmetry. You can only move. Actually, you do break spontaneously the SU2 are symmetry because you're moving in this direction. But when the brane is sent to infinity, you restore this SU2R, the SU2R symmetry. So the SU2R is on. So the general strategy is again to start with this initial configuration. And then we have the Bohr volume theory of D6 ending on D8. So the low energy, so we can treat the low energy theory of this system is basically 10-dimensional. Sorry. With action, which is given by this one. And then we can look at the SUSY variation of the gauge unit. In this case, is given by this. Epsilon is the parameter of the SUSY variation, so it's a spinor in 10 dimensions. And we can set this equation to 0. So we can find the vacuum solution of this. In particular, we want to specialize this 10-dimensional limits according to the symmetry of the background, which is given by SO5 times SO3. So the SO3 direction of the gauge field will become scalar. So, but I goes from 7, 8, and 9. And moreover, they will depend on the 6th direction. So we can solve the SUSY variation. And the SUSY variation, posing SUSY.
So the word volume theory of the D6 ending on D8 has a gauge field?
So this is, so we can treat the system of D6, D8. The Bohr volume theory of D6, which is like intersecting the D8. And so we're basically looking at the boundary condition of the D6 ending on D8. And you can basically model this system as 7D Yamis with 3 orthogonal scalar. Where this 3 orthogonal scalar, by solving this SUSY variation, you get this basically this equation, which is the NAM equation.
So you're not okay. You're not right. Okay, this is like not reducing to a 6D theory. You're
no. This is just looking at. This is just. I mean, I'm just highlighting the general strategy to look at this. This part of the theory. This part of the theory will tell us about, generally about how to send the D6 brane to infinity. So to speak.
So just to be clear, this this field strength that you write down, it has a dependence on the 7th direction.
On the 6th direction, yeah, this is the 6th direction.
Okay, okay,
Yeah.
Thank you.
So the solutions are classified by this. Actually, are given by this. So the solution of this equation is just the solution of the NAM equation, where T are the generator of the SU2 embedded into the flavor symmetry. With the flavor symmetry, I mean the group given by the number of D8. For example, for this is an example for SU the number of D8. So we the solution tells us that the solution are classified in terms of embedding or of SU2 into the flavor symmetry given by the D8. And the solutions are classified by nilpotent orbits. So these nilpotent orbits are basically given by this embedding, the embedding of SU2 into G flavor. And what tells us geometrically is that the D6 geometry is basically merged into the D8 geometry in a sort of finite solution. So this happens for like any DP plus 2 brane system. So the DP brane, it goes into the DP2 brane and it forms a final solution. And in particular, we want to enumerate the solution of this equation. This will be enumerated by the Young tableau. So if we have if we start from this configuration, we can have solution which are loaded by two Young tableaux. So we have a system on the right and a system on the left. So we can send this X brane to infinity on the right and on the left. And the theory that you get will be basically labeled by this Young tableau on the left and on the right. So these are just two examples. And moreover, there can be also other brane manipulation. One can send the one D6 brane to infinity in the 6, 7, 8 direction, or one can send like a D6 brane together with an S and S5 brane, and this will give access to like a mixed branch. Okay, but then we talk about holography, and in particular, given this brane system, one can now try to find holographic solution of this system. Holographic solution, I mean ADS7 solution, which are dual to this brane system. And the solutions are found by solving the supersymmetry equation on type 2A supergravity in this case, which are so this is how practically one should approach this problem by solving this equation. But pictorially, the solution actually are very simple to understand, and they are given by, so if we collapse all together the NS5, so these are N and S5, and we collapse all together, and then we have D6 brane coming in on the left, and we have this funnel on the right. So this brane will back react on this S3, which is an S3 embedded in this 6, 7, 8, 9 direction. So this brane will back react, and the near horizon geometry will give a deformed S3 solution. So where the D8 brane will wrap to the D8 brane, check the screen. This is D8 wrapping S2. So this geometry is basically an S2 fiber over an interval, which is parameterized by coordinate Z. And the brane will back react on the geometry, so we will get D8 brane wrapping this S2, and also D6 brane, which are point light. D6 brane. So this is the solution, and the metric schematically looks like the following. So this is the metric. So it's a work metric, so we have work ADS7, and we have also some working for the Z and S2. And all these functions, they depend on a single function, alpha Z, and alpha Z, where Z is the coordinate of the interval. So they basically depend only on one coordinate. The flux, so F0 is constant and can jump at D8 location. And the F0 also can jump, so like this. And F2 is just proportional to the volume of the two-sphere, fiber over the interval. And H is basically proportional to the volume of the three-dimensional space, which integrated gives the number of NS5 branes. But if one solves this condition, so this is not all to specify the solution, we need to specify this function. And this function is specified by solving this condition. And the equation that one gets is the following. It's a very simple equation. So it's in terms of alpha. So it's an ordinary differential equation which can be solved very easily. And the solution of this equation will depend on some boundary condition. And the boundary condition will be boundary condition at the poles. So there can be irregular poles. Or there can be like D6 brane poles. So where the metric of close to the, for example, if you have a D6 brane at this point, the metric will look like similar to a D6, to metric of a D6 brane. By solving this equation, we can obtain what is called the rank function. A rank function is basically this just integrating once this equation. And the rank function is piecewise linear, and it moreover is continuous. So we don't want like weird metric singularity. So we want this Q to be continuous. So the rank function is basically given by this solution. And we can see, so this is an example of rank function with changes. So this first derivative can be discontinuous by this equation. So when F0 changes because of the presence of the D8 branes, it means that the slope of this rank function changes. And so the slope is given by this. So the different. So Ri are basically the rank of the. So I would call a rank. So because this is a rank function, but what they correspond to, and they correspond to the actual quiver. So from this solution, from this rank function, is easy to read off the quiver of the tensor range of the dual SCFT. So we can, so this rank function will correspond to this brane system. And so this is in terms of this nilpotent orbit of the H-plane. So this is just an example of a more complicated rank function. But the important information here is that this rank function, from this rank function, you can really read off the quiver of the tensor branch of the dual set. And so given this solution and given this, there seems to be a really nice correspondence with the dual 1,0 theories, we can actually compute holographic observables. For example, we can compute, so first of all, a CFT is specified by a set of primary operators. Primary operators is given in terms of quantum numbers, where J1, J2, J3 are quantum numbers of SO6 embedded into SOSP8, and then there will be the SU2 R symmetry. So we specify the SU2 R symmetry quantum number, and delta is the scaling dimension. So yeah, which is the information about the dilatation of and the scaling of the CFT. And moreover, there are also this is not all, so that you can what specify a CFT is also a set of correlation functions. Okay, now the ADS CFT, the boundary theory. So the theory, so in ADS there is a boundary. And the boundary will have the same isometry of ADS space. And we can couple this boundary to the bulk in this way. So this is the blue one at bulk field, and the black boundary operators. Moreover, by this coupling, you can see that a gauge, so a conserved current of a global symmetry in 6 dimensions can be coupled to a vector of the bulk gauge theory. So bulk gauge symmetry will correspond to a global symmetry in the 60 dual, in the 60 dual. Okay, so these fields are basically classical, so the classical configuration in a DSM. And at the boundary, there are sources for the operator. And in particular, one can solve this classical configuration. And this classical configuration, yes, they will come with a mass, which for a scalar is equal to. So there is a relation between a scaling dimension and the scalar in this way. Okay, but how do we, so given the background, so given the DS7 solution I described before, how we can get this operator that couple at the boundary, we can get this classical field configuration that couple at the boundary. Well, there are two main strategies. The first strategy is to study linear perturbation. For example, we pick up the metric, we perturb the metric, and we just make an ansatz of the metric because the metric is given by an external DSM space times an internal space. And this is the standard ansatz. So why? So these are the coordinates of M3. And now we plug back these ansatz into the equation of motion. And by plugging into the equation of motion, what we get is basically the following equation. We get a Laplace equation for this function 1. And this is the Laplace operator. On M3. And M computes actually just the scaling dimension of the operator via this formula. The second strategy would be to study fluctuation of branes in the background. So for example, we can study the non-abelian fluctuation of the 6 brane, and this will lead to the, holographically, to the X branch operator. Or to a subset of X branch operator. Moreover, like one can study fundamental string stretching between like D6 brane and D8 brane, or stretching between 2 D8 brane. And this will lead to mesonic operator. So we write just a chain of hypermultiplet. And the D0 instead will give rise to baryonic hypermultiplet. So these probranes also describe operators of the dual safety. Finally, as a last last good test for this duality, one can compute the Weyler-conformal anomaly. So what is the Weyler-conformal anomaly? So in a CFT, we have a stress energy tensor, which on a curved background, so the trace is the stress energy tensor. If we couple the CFT to a curved background, it's not zero anymore. And in particular, it will be given by this A plus CI. So the E is basically the Euler density of the 6-dimensional space-time. And I are some bytes. So let me focus on A for the moment. So A, so first of all, it appears in the 4-point function of the stress energy tensor. Moreover, is actually a good measure of degrees of freedom due to superconformal field theory. So it's like a nice observable, the superconformal field theory. And finally, in this paper, this very nice paper, it was shown that A can be given by a combination of Toft anomalies, which are computable by Toft anomaly matching at low energy. So this quantity can be computed theoretically and can be matched to a gravity dual computation. So what is the gravity dual computation? So the gravity dual computation, so we start from a 7D supergravity on this background. So we deform a little bit the DS7 background in this way, and we deform the metric in this way. So this deformation is given in terms of an expansion so close to the boundary. So when the boundary is at equals 0, close to the boundary, it will be an expansion of the power expansion or logarithmic expansion in terms of rho. And if we integrate in a DS7, there will be some divergences, but these divergences can be subtracted by a so-called procedure, which is the so-called holographic renormalization. So these divergences will basically be proportional to covariant tensor of the 6th-dimensional space-time, and we can add like a counter term for this covariant tensor and cancel these divergences. But a finite term will survive, and the finite term will be the following one. So the finite term will be proportional to so where this is the dilatation transformation in this background. So A is equal to L and then 16 G Newton times the other things. And this quantity in particular depends on the internal space. So in our case, it was M3. So we can compute this quantity holographically. So holographically, what this corresponds to is, so this is basically M3. Because so this is L5. L5 is basically our working factor. So L5 was equal to E5A, and G Newton 7 is equal to G string minus 2 times volume 3. So by plugging in this back into this, we get this formula. So we plug this into this, and we get this formula. And we can express in terms of alpha, and in terms of alpha is square alpha z alpha, the second derivative of alpha. So this is a very close expression in terms of this alpha function. And as a last comment, this quantity actually matches with the dual CFT in the following limit. So if we, for any solution, if we compute this quantity field theoretically, and we send the number of an S5, so the number of tensors to infinity, the number of the rank of the gauge group to infinity, but keeping the ratio fixed. In this limit, this will be equal to 8.1. And this will be equal for any solution. So giving a good test of this ADS dual being, of this ADS solution being the dual of this 1,0 superconformal theory. So, and with this I conclude. I also have some exercises. But yeah, that's what I wanted to say. Any questions?
Thank you, Fabio, for the great lecture. And yeah, are there any questions?
Maybe I can ask a question.
Great.
So, so you mentioned that the Romans mass in type 2A does not have M-theory lift. Is that supposed to be like a significant claim, or just I mean? So you're saying that if I compactify the theory to lower dimensions and use the usual, you know, type 3 M-theory duality, it will not work out with the Romans mass? Like, how should I think about this? As
No, it actually, no, it changed. I mean, you cannot go to M theory, but you can also, you can go to other dual frame. For example, I think you can go to type 2D.
But you're saying that the usual type 2B M theory duality will not work out? M theory on extra torus.
Well, yeah, it depends on which duality you. If you go back, then it doesn't work out. But if you do other duality, so if you do T-dualize in other direction, that might work out. But then you might change the dimension of the theory.
I see. But I was wondering if there's some kind of topological obstructions for realizing this kind of theory that involving a non-zero Romans mass within M theory. Or are you saying there's a dual description in M theory?
There is not, I mean, as far as I know, there is not a dual description in M theory, but for example, there is a dual description in F theory. So you can T-dualize, you can compactify one of these 7, 8, 9 direction, a circle, and T-dualize along that. And then you get a system of these 7 branes. I'm gonna talk about this 7 brane system a little bit in the third lecture. But you cannot go back to M theory then.
I see, thanks.
You can go back to M theory, but then you're changing the dimension. For example, you can go to 5-dimensional system.
Right.
Or to a fake 5-dimensional system. It's really a 6-dimensional, but it looks like 5-dimensional. I also going to talk about this in the third lecture.
Let's see. Any other questions? Oh, so there's a question in chat. Are there dual 2B systems to 2A with Romans mass?
Yeah, definitely.
Let's see.
Yeah, it's just, yeah, I didn't have, I mean, I wanted to include this, but I mean, you can just, as I said, you can just pick a circle in one of these orthogonal directions and dualize. What you get is the D6 will become D7 brane because you dualize an orthogonal direction. And then the intersection, so where the NS pi will become just intersection of D7.
Mm-hmm. Are there any other questions?
And can I ask about the Weil anomaly?
Yeah.
So the so it's a correspondence of the subleading terms are confirmed, or?
Yeah, subleading terms are. This is actually a nice question. I mean, one needs. If you do this holograph, so if you compute this holographically, like without any correction to the solution, then The subleading term, they don't need to match. So just the leading term matches. The biggest one at large, NS5 and D6s.
Mm-hmm.
But then the strategy, one strategy is to, for example, to compute correction into it might be hard, but like alpha prime correction, for example.
So you mean in the supergravity side, it's the subleading term in large N, right?
Yeah. So that term, so the subleading term might be corrected by alpha prime. That's for And then in order to match, you need this, right? Because, well, I mean, or
right,
you can do some. You can now use another strategy, which is, I mean, it has a flavor holography, but you can just use the brain system and compute like an inflow action from the brain system. And that should give you the right result. But for 2A, it's a bit more complicated because you have these many ingredients. And from M theory, this is done by Cantaro, UG.
Okay, I see. Thank you.
Yeah, the subleading term should be like an opportunity to learn more about string theory and holography.
Yeah, that's the other perspective. So that many people take at the moment. So they use CFT, they use bootstrap technique, for example, to learn about the quantum aspect of string theory. So using the CFT to compute something about the ADX tool. This is like another very nice perspective.
Any other questions or comments? Okay, I think our timing is good. So we have time for about a half-an-hour break before the next lecture. And let's thank Fabio again for the wonderful lecture.
Thanks.